Yeah, yeah.
I'm very thankful to the organizers for giving me this chance to bore you with this, and bore some of you for the second time or maybe the third time with this. See, when I was asked to give this talk, I chose a slightly different title. But then, you know, I realized that the company is such that it is better for me to be silent. And I remembered that a very famous Sanskrit verse which says that there is one freestanding, self-contained, pure virtue, that of silence, especially when there is an audience of people who know a lot. So I decided to be silent on that. But I would like to talk about this, which is somewhat of the sort of electron-based theme of this school. And also, I'm a little hesitant about this because I'm a little bit rusty on this. So please correct me wherever I go wrong. Okay, so this is about, this talk is about Ginzburg Landau-like phonological theory for emergent D-wave high temperature superconductivity in the cuprates. Now, of course, this subject is not an unfamiliar one. I think many of the people in the audience and perhaps a good fraction of the community of condensed matter people has been working on this for the last quarter of a century. There are very strongly held views. There are more than 100,000 papers. Well, many people believe that there is no clear-cut solution yet. Okay, so I will start with very briefly giving a background to sort of rationalize what we started doing, which is that we have a theory which superficially looks like the Ginzburg Landau theory for superconductivity. The Ginzburg Landau theory itself was developed in 1950. It's a continuum theory in which the great authors assumed that the superconductivity is described by a complex field which is psi of r, and this psi of r was identified later with the Cupr pair amplitude by Gorkov. Now, what they assumed could be described by a free energy functional, which is of a very simple form, a psi square plus b psi 4 plus c grad psi square, where a, b, and c are inspired by experiment. Now, in the mean field theory, for instance, the superconductive transition temperature is where a changes sign, and the only relevant degrees of freedom are the uniform value of psi. Now, what we had done many years ago was to propose and work out the consequence of a lattice free energy functional, which is somewhat similar to this, and this is somewhat late, you see. I mean, this is about 3 decades late, but then, you know, it's also a step backward because, you know, people know all about electrons, perhaps maybe in such systems, and certainly they know all about the Bardeen-Cooper-Schrieffer theory of superconductivity. So at this late date to start something phonological looks a little strange. So what we did was to do it in the hope that taking a step backward might possibly move the field a little forward. Okay, so what did we start with? We started with, as physicists do, or at least as most physicists do, saying that superconductivity resides in the plane. The cuprate consists of a stack of weakly coupled planes. So to the zeroth approximation, forget the weak coupling, and so concentrate on one plane. On this plane live copper atoms shown by blue circles. They live on the sides of a square lattice, and this is oxygen. We have to make some assumption about what would be the analog of psi of r, and our assumption is that we take psi ij, where let us say I and j are the nearest neighbor sites. The Cupr pair amplitude involving these two sites, which is a complex number involving a magnitude and a phase. Of course, this pair of sites can always be represented by a point at the center of these two sites. So what we do is to describe the free energy of the system as a functional of this object. And in the spirit of Ginzburg and Landau, we describe the free energy as a sum of two terms. The first term just is like a psi square plus b psi 4, and it is in this notation a delta m square plus b delta m 4. And if the mean field theory were correct, then the place where A goes to 0 is some transition temperature. It is the mean field transition temperature. We identify it with the bare pseudo gap line. Then F1 is the lattice analog of the grad psi term. It is C psi star psi m, C psi star m psi n, and the complex conjugate. And it looks like this. What we are saying here is essentially that the long range order, which is actually the long range phase order, that develops as a result of this interaction, and it will develop as a result of this interaction. For instance, if C is positive, you will have a D wave superconductor, a superconductor with D wave order. So in our picture, yes, there are preformed spin singlet Cupr pairs because of essentially, well, in microscopic terms, because of the presence of a large nearest neighbor antiferromagnetic spin coupling. But there are no preformed D wave Cupr pairs. D waveness develops as a result of this interaction. So it's what we call everyone such things are called emergent properties. Okay, so that is the idea. And in terms of a more familiar spin analogy, you see delta is like the length of the spin, phi is the angle of the spin with the x-axis, and the free energy functional F describes the thermal probability of spin length, and F1 describes the nearest neighbor antiferromagnetic coupling between these spins. The T mean field is at some temperature T01, which in this figure I have shown by this straight line, because we wanted to, and we want to keep things simple. So we we have to say something about what A is as a function of temperature and doping. We took one of the simplest possibilities, which is to say that A is a straight line which has a certain value at x equal to 0 and goes to 0 at some value of x. So this is the whole doping plane. So this is the, you can say that this is the bare mean field transition temperature. Or this is the bare T star in our language. The blue curve is the, from this Ginzburg Landau functional, you will get a blue curve where the superconducting stiffness becomes non-zero. That is the temperature at which superconductivity appears. Of course, this is bad, certainly near these 2 points where quantum fluctuations are especially important. And we have included quantum fluctuations, and we find that indeed their effect is to change this curve to a more reasonable parabola. Okay. So this is the idea. So let me just repeat what I said very briefly. See, in the original Ginzburg Landau theory, that was meant to be sensible near the superconducting transition temperature. It was meant to be qualitatively descriptive of the superconducting transition. In this approach, we are trying to see if this can describe all physical properties connected to superconductivity at all temperatures, for all hole doping, for all systems, and it is qualitative as well as quantitative. I mean, our idea is to start with a relatively simple functional, and to be able to make sense of as large a number of physical properties as possible over as wide a range of temperatures and hole doping, and for as large a number of systems as possible. So this is the idea. It is somewhat obviously too ambitious, and that is what that says. Now, what is the input? The input, again, as I said, we try to keep it simple. We say that T star is a straight line, characterized by one energy scale, and then, okay, so this is the, so these are the three inputs. You see A, B, and C, because the functional depends on these parameters, which in a phonological theory have to be put in by hand. So we put in A as something which goes to 0 along this line. When this becomes 0, so in the Tx plane, that is where A goes to 0. This exponential factor simply suppresses fluctuations in the order parameter, which unfortunately are artifacts of this classical fluctuation theory. You know, the system is actually a highly degenerate quantum system, and fluctuations are suppressed because of that quantum Fermi system. So because of that, fluctuations are suppressed, and this is just put in by hand to achieve that. Then B, which in energy units is this, C is energy units is this. There is a factor X or hole doping slipped in here. That is because experimentally it is known that the observed superconducting transition temperature is roughly proportional to hole doping for small hole doping. Now, our calculation shows that Tc is proportional to C, and since Tc is proportional to X from observations, we put C as being proportional to X. So that is where this comes from. And well, there is a lot output, some of which I will show, consists of let us say the local thermal Cupr pair amplitude or gap, onset of a non-zero phase stiffness or Tc, superfluid density, specific heat, vortex structure, electron Green's function using this Cupr pair amplitude coupled to electrons, which requires an even more questionable hypothesis, which I will come to. So this slide shows the average local Cupr pair amplitude as a function of temperature. You see, this functional says that there is always some probability for this length to be non-zero at no matter what the temperature is, and that's what you see here. That you see, for example, at one doping, the topmost line. The topmost line shows how the probability of yeah, I'm having some difficulty pointing. Okay, so it shows how the probability of the local Cupr pair amplitude depends on temperature. So as you increase the temperature, it becomes smaller, but it is never 0. So it is not that suddenly there are no Cupr pairs and then suddenly there are Cupr pairs. So there are Cupr pairs at all temperatures. Their amplitude becomes smaller and smaller as the temperature increases. So from this, one of the things we do is to find, let us say, the location of the maximum slope. That is, for a given curve, where is the maximum slope? Identify it, for example, with the pseudo gap temperature, and plot it. Which, if I have the time, I will show that.
Excuse me, how are these curves obtained?
You get it from the functional. Okay, so the functional tells you the probability for different values of delta m, and then you calculate the expectation value numerically.
Oh, okay. So this is sort of like a Monte Carlo.
It's a Monte Carlo on a finite 2D system. And then we look to see if there are finite size effects, and then we do the orthodox things. Okay, so this curve, for example, shows what the initial or the bare pseudo gap line is, and it shows several versions of the inferred calculated pseudo gap line, numerically calculated. One is like this. For example, if you were to turn on the phase coupling term, which you do often experimentally by turning on a huge magnetic field, then you would get this pseudo gap line, which sort of enters this TC dome. On the other hand, if you did not turn off the phase coupling term, you will get a pseudo gap line which falls like this and then hugs the TC line. And of course, there have been many learned articles on pseudo gap, friend or foe of superconductivity, and various kinds of pseudo gap types and so on. And this is our take on what that could be due to. Okay. We have also calculated the superfluid density as a function of both temperature and hole doping. And the superfluid density in this functional is just the second derivative. You know, you put a Peierls phase factor, take the second derivative, and you get this number for the superfluid density. And this you calculate numerically, and that is what has been done here. So there are several curves here. You know, one curve shows the sort of cluster mean field theory for where the superfluid stiffness becomes non-zero. Another curve shows, for example, the zero temperature superfluid stiffness, that is the green curve. It shows the zero temperature superfluid stiffness as a function of hole doping. And there is an inset there which shows how the TC in the cluster mean field theory and the zero temperature superfluid stiffness vary, and this is you know, well known in the literature as the boomerang curve. Okay, so we have also calculated, because the classical statistical mechanical model, you know, in which the free energy is a function of some classical variables delta and phi. We can calculate the energy of it, we can calculate the specific heat and so on, and we have calculated the specific heat. And here I show in particular the specific heat near TC. The specific heat also has a bump, which is a sort of gentle bump near T star, because of the fact that the magnitude fluctuations, that is the fluctuations in the magnitude of the Cupr pair, don't cost that much energy there, and so that gives you a bump. There is a sharp peak near TC because of the phase fluctuations being low energy and phase ordering, incipient phase ordering. Now what this curve shows is, you know, if you put some flux in each plaquette, what happens to the specific heat? And this shows what happens to the specific heat if you put increasing amounts of magnetic flux in a plaquette. And it shows the broadening which has been observed experimentally for unusually small magnetic fields, and the numbers we calculate are in good agreement with what has been observed. This is a picture of the structure of a vortex, namely if you just take this functional and are at zero temperature, it's an energy, then you insist that there is a vortex at some point x equal to 0 in the middle of a square, so that the phase changes by 2 pi if you go around that square, and that's all you insist on. And then you use this energy to obtain the magnitude and phase of the order parameter at every site on the square lattice. And what is plotted here is the magnitude of the order parameter on the square lattice at different points, but those points are not shown. But what we are supposed to see from here is the fact that the magnitude very far away from the vortex is suppose 1, that is at the top. Then you notice that the magnitude even near the core of the vortex doesn't become very, very small. It is about 0.75. So this is this is well known in the field. It's a Josephson vortex, a phase vortex, and this is the calculation for x equal to 0.11, that is relatively small hole doping below optimal doping. For large hole doping, we have done a similar calculation. We find that it is very much like a BCS vortex, that is the order parameter near the vortex core becomes very much the other thing, so far you see there are no electrons in the theory. It's only pairs, fluctuations of Cupr pairs and so on, and how much energy it costs for fluctuations and interactions between them and so on. So when I talked about it with some people, they said, oh, what about electrons? So, well, this is our first essay. I mean, first attempt to introduce electrons into the problem, because most of the a very large number of measurements are, for example, of angle resolved photo emission or STS and so on, that is involving coupling to electrons. So what we did was something like this. We assumed that what we wanted to do was to find what happens to electrons moving in a medium of such fluctuating Cupr pairs. So we couple an electron here to the fluctuating Cupr pair, which is shown by a wavy line, and so this fluctuating Cupr pair actually consists of an electron and another with momentum minus k plus 2q. So that gives you a fluctuation 2q, and then of course there is a recombination here to finally give you an electron back of the same momentum k. So this is a quantum mechanical process. We have calculated self energy involving this. The self energy, unsurprisingly, is of the form which has 3 terms. This is the form factor, which, for example, if you had long range d wave order, this would be like cos kx minus cos ky. Then d is the propagator of this Cupr pair fluctuation. P you can think of as this vertex and that vertex. And G is this propagator. And so using this and using the pair correlation function or pair propagator from, let us say, the Kosterlitz-Thouless theory, we have calculated this self energy, and from that we have calculated the single particle spectral density. And well, this is a figure of the single particle spectral density for different temperatures as a function of energy for a particular doping point 1, at which the Kosterlitz-Thouless transition temperature is 66 Kelvin. Now, what this is supposed to show is shown in some of these slides. It shows Fermi arcs. It shows that these Fermi arcs depend on temperature. And so we have plotted the length dependence of the Fermi arc as a function of temperature. We have also plotted the temperature at which the Fermi arc reaches the edge of the Brillouin zone, and that when shown as a function of hole doping is the well, it is the pseudo gap line. We have also calculated below the superconducting transition temperature something called band bending. That is, if you include the self energy in the electron propagator, then and then you calculate the sort of positions of these peaks in the spectral density and plot that as a function of k or angle, you find that it is not, I mean, if it were cos kx minus cos ky, it would be a straight line, but there is a very significant bending of the band, and this band bending increases as temperature increases and becomes well, there is as you go above Tc, well, there is a Fermi arc. So it shows here, but at 0 temperature there is no band bending. This is essentially because of the fact that the electrons are coupled to what you may call spin wave like fluctuations of the order parameter, and that changes their energy, and at the near the nodal point the gap is anyway very small, and because of its smallness the band bending is the largest there. Okay. So let me nearly conclude. You see, one of the things which well, this phonological theory already ignores many things. It ignores other interactions. It ignores other bosonic fields like spin. So it doesn't have anything to say about the competition between antiferromagnetism and superconductivity. It doesn't include other low energy degrees of freedom like lattice vibrations or unpaired fermions, which are also very low energy degrees of freedom. So therefore, it doesn't and cannot address at the moment competition between superconductivity, antiferromagnetism, stripes, 4 into 4 superstructure, liquid crystalline correlations, charge order, etc., etc., etc. So our aim was not primarily to, at least initially, not to get entangled with these very important issues, but to see whether a simple phenomenological theory with only Cupr pair fluctuations as the degrees of freedom can describe a large variety of experiments, both quantitatively and qualitatively, and we believe that that is what has happened. Of course, there is a wish list which is here. We would like to understand quantum oscillations, transport effect due to pair fluctuations, etc., etc., etc. And fortunately, some of this wish is being fulfilled. One is Kingshuk Sarkar and Subrata Mukherjee. They have calculated recently the magnetization as a function of temperature above the superconducting transition temperature, and the magnetization above the superconducting transition temperature is due to these Cupr pair fluctuations. And we do find that this magnetization has the same sort of dome form as TC, but well extends to somewhat higher temperatures, and this is also not, I mean, this is almost exactly what is seen in many experiments. We have also started, and Kingshuk has done some calculations for the Nernst effect. The calculations are not complete yet, because we have done, for example, for magnetization, the calculations have been done for about 7 values of doping. Here, the calculations have been done for about 3 values of doping: underdoped, optimum doped, and overdoped. But the trend is somewhat similar. So this brings us to the question of what about a real theory? Because it's a phenomenological theory, and people are sort of switched off by such things. So there are no electrons in a serious way in this theory. So the thing is whether how do you go about getting such a theory, and whether if you did have such a theory, then would it look like, would the Ginzburg Landau theory, in which you insist on integrating out all other degrees of freedom, would it look anything like what we have done? I don't know the answer. So I just want to mention 2 things which seem to suggest to me that if we have a real theory involving electrons, that is more likely to be a strong coupling theory than not. And the first is the fact that we know that there is experimentally a very large antiferromagnetic superexchange coupling, at least at 0-hole doping, which is surprisingly large. And it is also well known that this is exactly equal to nearest neighbor Cupr pair attraction. The other thing is that we have introduced a term which really does all the trick, which is a coupling between these Cupr pairs, nearest neighbor Cupr pairs. And this term again is much more reasonable in a strong correlation picture due to the diagonal hole hopping T prime. I mean, if a hole were to hop diagonally from one site to across to the corner site in the square, then you would couple the nearest neighbor Cupr pairs along the x and y axis, for instance. So, and the coupling would be proportional to T prime, and in a strong correlation picture it would be proportional to x T prime. And therefore, the fact that we are able to make some sense of data is itself a strong indication that this may be there. Interestingly, there long back, two people in the audience and many others did an electronic structure calculation, and that found that the diagonal hopping amplitude, and which has a much larger energy scale than Tc, was proportional to Tc optimum across several members of this cuprate family. So this seems to suggest to me that maybe strong correlations are actually involved in this process. So, all right, let me summarize. We have developed and looked at the consequences of a phonological Ginzburg Landau-like lattice theory for high temperature superconductivity in the cuprates with nearest neighbor Cupr pairs as the basic low energy degrees of freedom. Then if we find that if the interaction between these degrees of freedom is antiferromagnetic, then D-wave symmetry superconductivity emerges. For electrons moving on the same square lattice in which the nearest neighbor interact electrons are the Cupr pairs, they have to couple to each other, and this coupling leads to low excitation energy electron spectral features which are seen in the R phase. I think there are some suggestions that a strong correlation theory would be natural for that. Thank you.
Yeah, thank you very much. The question and discussions. Andy.
Thank you. So the new feature of your theory is a bond superconducting pairing order, then coupled across different bonds.
Right, right.
Presumably this has implications for collective modes of the superconducting phase.
Yeah, I mean,
what are they?
I mean, there are conventional collective modes, then there are internal modes. Yes.
Have they been worked out?
No, not yet. Internal modes would be gapped, but they have not been worked out.
But they should be visible.
Yeah, there should be. And their consequences could be very important. Certainly above Tc, they will be very important.
So from the, towards very fast actually, you showed a diagram actually, the phase diagram, where you have like superconductivity as well as some antiferromagnetic. Was that schematic or?
In reality, yes. There is, okay, I mean, if you want, I can show a pretty picture, which is this. And this picture does show that there is antiferromagnetic, there is an antiferromagnetic phase and there is a superconducting phase. So we really have nothing to say about this. We pretend that we are somewhere here. The holes are, because the holes are mobile, you don't have to worry about antiferromagnetic correlations. But yes, if you want a more comprehensive picture, yes, you have to include those issues.
Can this be like if you start with say this free energy, like some kind of alpha m square plus?
Yeah. I mean, that is the obvious possibility. The obvious possibility is that in the free, if you stay phenomenological, the obvious possibility that you put a term like Si dot Sj in the free energy functional, then couple this to the Cupr pair degrees of freedom, and then run and see what happens.
So in your first, I think, couple of slides, you showed a graph between delta and T.
Right.
So
Sorry, let me come to it.
So this delta is basically the binding energy of the Cupr pairs, roughly speaking. Is it?
Well, yes, this is thermal average of this magnitude.
So the numbers 80 and so on. Are these anywhere near to? Are they physical to take?
Which numbers?
Delta value of delta to be around 80 milli-electron volts.
Yeah, they are physical.
And they just seem to continue forever. I don't know.
Yeah, they do, but nobody knows yet, for or against anything about this.
Yeah, but any physical. So how done?
But you see, look, it is like this. This is the average. But thermal ionization of these Cupr pairs is very, very likely. So we were not saying. Suppose you think of Cupr pair as some entity. What is its lifetime? We are not saying anything about it. So you may have a Cupr pair, but it may not live
So this delta is somehow related to, no. So the first thing is that we should have a Cupr pair, right? To start with.
That is the assumption. The assumption is that because there is a experimental evidence for very large J from inelastic neutron scattering in undoped cuprates, and that J implies unquestionably that there will be an attraction between the nearest neighbor electron pairs. So the belief is that, so that is where we start from. We start from saying that this is the basic object. The basic object is these pairs.
Can it be translated to BCS in some form? I mean, just to say.
No. The reason is that we are familiar with something else which we don't question, which is the magnetic transition. Suppose you have an Heisenberg antiferromagnet or a ferromagnet. There you don't ask where does this spin come from. All you ask is, well, they interact in a certain way and give you a certain long range order. So here what unfortunately you have is a situation in which the spin formation temperature is not that terribly high and it changes with hole doping, and then the spins order. So it is not exactly a spin system and it is not exactly a BCS system. In a BCS system, the ultimate limit is the spin forms and orders at the same temperature.
Do I understand correctly that what destroys the long-range ordering in this approach is phase fluctuations, basically?
That's it. Phase, what describes long-range order is non-zero phase stiffness.
Yeah, but what accounts for the, I mean, if we go back to your two lines, the pseudo gap, right, something like this, right? So what accounts for the difference between the blue and the red line, which is TC, is basically phase fluctuations.
Basically, I mean, it is very clearly the phase fluctuations for small doping.
Yes, yes.
But then at larger doping, they get coupled to each other very strongly.
Yes.
And
yeah, I'm talking about the small doping
in
region.
small doping, it is a phase fluctuation.
So how do you make this consistent with, I think, various experiments that have tried to identify the range of temperature above TC where there is significant phase fluctuations and which is not so large? For example, there is there are several such experiments.
Yeah,
right?
there are, and that is why I tried to show this curve. You see, this is in our picture, we would believe that there is a fluctuation magnetization, and so we have calculated fluctuation magnetization for different hole dopings in different temperatures, and this is what we find, and this is what many experiments find. Now there are many other experiments. For example, Josephson
proximity effect between an underdoped and an optimally doped IBCO.
Right, right. So yeah, we have to visit them. But at the moment, this is what we believe. We believe it on the basis that we have been able to make sense of a large number of other experiments.
And again, what is the, again, if you go back to the blue and the red line, how is the pseudo gap blue line identified in this approach?
Yeah, it's a crossover. There is no phase transition there.
Sure.
So the dotted line is the sort of bare pseudo gap, and
so that's when delta M appears or something, right?
There delta M, I mean, there by construction, is a delta M square, and delta M square has a coefficient. I ask where does it go to 0, and it is sort of engineered to go to 0 there. Okay. Then I take this functional and ask where is the temperature at which the local pair magnitude has the maximum slope as a function of temperature, and then that is a slightly different temperature, lower temperature. It's lowered because of fluctuations.
Yeah, very interesting discussion, but let me move on to the next speaker, and let's thank the speaker again.